No, it's...
I don't think you end up creating porous channels. It's just to better fit biology. If you have some molecule that the cells actually consume on the outside, like it binds with something on the membrane, then you could use uptake just outside, and because that makes sense with the biology. If you have something that comes in, well, maybe it indeed diffuses through the whole cell and there are organelles everywhere consuming it, or you could have specialized stuff just on the border inside, and that consumes it. And there's also the option of the center of mass, which I guess could be something to do with the nucleus of the cell, if you assume that the nucleus is the center of mass. But yeah, those are just for biology's sake. I'm gonna skip the just outside the boundary because that looks basically the same as the previous one. And the one at the center of mass, now there are several dots of 0 in the middle of every one of them. But yeah, those options are just to better fit biology. Yeah. Let me do one step. Then let me come here. Diffusion solver, fusion data, 0.0. Template. Stays. So those are the options for the uptake. And the note that I already made, that the cells uptaking stuff is going to change the concentration profile outside the cells as well, unless it's the medium itself that is providing things. And here's the table again, where now the cells also have a uptake region that you can set as a parameter. And now the actual tree-layered tumor. Yes, yes, there is uptake on contact with. I'll add those options to the simulation today. Okay, so this is another hands-on example where I have the tree-layered tumor still with the cells frozen. So this one is on examples avascular tumor B1 profile. Oh, lovely. That's the issue. Yeah, I just changed this initial size of the tumor. And apparently I made it too big. Okay. So since I was here on the XML, this is the blob initializer, one of the 2 ways to initialize cells in the XML. So a blob initializer initializes cells to a circular or a spherical shape. And you set its center, where you want the cells to be, the radius of the circle you want, the gap in between cells inside that blob, and here 0, but I could leave 4, 10 voxels in between them. The initial widths of each of the cells, because they are gonna be initialized as squares or cubes in 3D. So the width is the side. And in here, the cell types. So I only have proliferating cells, but I could have proliferating and necrotic cells. And say I want to have about 30% of them being necrotic and 66 being proliferating. I just type proliferating twice and necrotic once. So the proportion of cells is going to be proportional to the proportion of types you have there. It has to be an integer that you set by hand there. But if you have some sort of parameter scan, you could add that to the parameter scan somehow. No. But it's a good idea. Have a in between A and B. So in this one, they do consume, but now they are not doing anything active, but they are eventually going to change type when the oxygen levels go low enough. So if I go to the actual Python code to start showing it to you. So first, I've set some parameters. The only cells that are going to uptake things are the alive ones. So I have the proliferating uptake and quiescent uptake. I don't have a necrotic uptake. I've used the same relative uptake for both of them. I could have done differently. But I'm not doing, these are just names for those numbers so that I don't need to hard code them afterwards. Because I'm putting here the relative uptake here. I could have just written down here 0.2. And that would have been fine. But if I have that in several places and I want to make my life easier, I have it as an actual parameter beforehand. So here I'm setting 2 oxygen thresholds for the change of type. Since oxygen is going from 100%, whatever that is, to 0, I have the proliferating threshold for them to turn quiescent to be 35% of the maximum, and for them to go necrotic, 20%. This I'm going through all of the cells and actually initializing their volumes and the lambda volumes. I'm setting their volume to be whatever volume they have been initialized as, but I could have written whatever. And since the cells are frozen in this simulation, this is superfluous because they are not going to change anyway. Let's see if they already changed type. Yeah. So for, I think, James, Julio, I think Zoom has frozen. Oh, now it's going again. There. Huh. No, yeah, now it went. It was lagging behind. Yeah. Yeah, we should do that tomorrow onwards. Yeah, it fixed itself. Thanks. Okay. So here is the uptake thing. I'm getting the field secretor for oxygen, in this case. Then I'm going through the proliferating cells, having them uptake, then going through the quiescent cells, having them uptake. But this cell list by type takes as many arguments as I want, so I couldn't have just done prolif and quiesce at the same time. And they would have been done, well, in some order, but some random order of both types. Then for the actual change of type, I'm going through the proliferating and quiescent because necrotic cells, since they are dead, they can't change anymore. So I'm going through proliferating and quiescent, then I'm getting the concentration at the center of mass of those cells. I'm going the field oxygen, XCOM meaning center of mass X, Y center of mass, and Z center of mass. Then if that concentration is less than the necrotic threshold, turn necrotic. If it is less than the proliferating threshold, turn quiescent. Else, turn back to proliferating. So now if you could open up this simulation and play around with the thresholds to see what happens and what not. So now you have a reference for the path of where the simulation is. Is that readable? Yeah. It is on the workshop page on the website. Then there is a link to the student's Google Drive. And in there, there is Avascular tumor class, examples, Avascular tumor, P1 profile. If you had already downloaded the zip file, I've made a mistake. And on the blob initializer, yeah, so the version that was on Google Drive up to 5 minutes ago, because my Google Drive probably synced again, this radius on the blob initializer was something like 150, and that's too big, and it's trying to build cells outside the region of existence. So yeah, that's on the XML at the very end, line 97. So yeah, just put that down to 75, or yeah, 75 works and still makes a big tumor. I'm gonna check the other ones. Yeah, the following examples also have the same mistake. Yeah. So just as I remember there, the assignment is to play around with the thresholds to see what happens. And the uptake rates, see what happens. And thanks to him, adding a plot of the population sizes. Change the uptake here, nor the thresholds, because the only things you can change in player are the things that you have specified in XML. So uptake and everything else is set up in Python. Nowadays, we can give any XML variable a string ID to make it easier to access in Python. So maybe you could create a block in XML user parameters with tags, and then each one of the ID to make it easier to access in Python. And maybe it would show up here, but I'm not sure that it would actually update the Python side of the simulation. To get the number of cells of a given type, since we already have no, but we do have no, but we also don't need the center of mass. So say I want to know the number of necrotic cells. So number necro, say I wanted to know the number of necrotic cells. I know that CompuCell can already give me a list of all the necrotic cells, which is this one I remember, but I may not. I can go to visit all cells of a sys Python, visit all cells of a given type, and click. It's going to paste the loop that goes through all cells of type 1, 2, etc. So the number of necrotic cells, it's going to be the length, which is a Python function, of the actual list of necrotic cells. So length of self.cell list by type, self.necro. One line, I know how many necrotic cells I have. It can, you just need to go into the options or configurations. Then you can set the background color and for it to match the parentheses. The theme, there's a Hello Kitty theme as well. Which is not great for contrast. So yeah, to change the theme and stuff, it's configuration, configure, Might be. I'll go there. Might be that. Yeah.
Oh, I see. I've got default, which is one kitty is bad, right?
Well, Hello Kitty is very pink and the contrast is not great, so it's amazing. Well, the default is white background, black letters. I prefer dark background. But to match parentheses, it's not on the styles, it's on the AI editing. Then you have everything. Pipeline is enabled to completion. Huh. Might be elsewhere. Yep. Well, I only have the cell field. So the cell field is done by default, but by default, it only gives you one cell field. But if you click on any of them, they have this drop-down list, which has the cell field and all the chemical fields you have. So it's just selecting that. And if I had, say, 5 chemical fields, I could just add more with that new graphics window button. And it's gonna just nope. Yes, because I had already made them and CompuCell saved the preferences. So if you go to actually the simulation folder, there's this settings.sqlite that has the stuff I did on my player and saved. And player saves those automatically for when you go back to that particular simulation. That's why I knew you'd have both plots already. Mm-hmm.
I'd like to say the red one is...
Yeah, that one I don't really know. Documentation for, you can try to search for PyQt graph, but I'm gonna warn you that the documentation of PyQt graph is not that good. But I'm sure there is a way. I think we've spent some time with frozen boring cells. We can start the final example, which is the same thing as this, but now with the cells actually growing and dividing. So if I now open P2, adding growth or medium as supplier, either or works. Looks about the same, the beginning. But now, instead of the cells being frozen, they are actually free to reshape themselves. And the proliferating cells are growing. And talking about growth, well, cells do grow, but if they don't grow forever, eventually they have to divide. So in here, there's also the mitosis and how to do mitosis in the code. I think we might go over that tomorrow. Just show here that it works and things grow, and eventually this tumor is going to reach a homeostasis size. So in this one, I already have the population sizing graph. So you can just copy it from the code of part 2. This is another bug, by the way, Maciek. The cell field or chemical field sometimes disappears. Then it's just a matter of opening a new graphics window. So yeah, for now, these proliferating cells are just growing for a bit, but soon enough, they are going to divide. The way I set it is that when they reach twice their initial volume, they divide. So in this case, the core of the tumor reached the quiescent limit before any division occurred. Yep. A division wave. And in CompuCell, to have division, we have to have a special separate class in the steppables. So this first steppable is the same as before. It takes care of cell types and uptake. But after this one, I have the mitosis steppable class. And this one, oh God. Okay, this theme is not good. Function names are the same color as the background. There we go. So this mitosis steppable, each step, it creates a list of cells to divide. Then I'm going through all the cells that can divide, which are proliferating and quiescent, just in case some cell turned quiescent just before we got to divide. I'm still allowing them to divide, but whatever. Then if that cell's volume is twice the initial volume that I have as a parameter somewhere, I'm gonna add that cell to the list of cells to divide. That append there.
Right here,
Yes. Yeah, yeah, all of the simulations have that mistake. Then instead of going through all cells, I'm going through the cells that are in the cells to divide list and telling it to divide. In this case, just to divide in a random orientation. But there are other options down there. You could specify a vector. You could make it divide on the major or minor axis of the cell as well. And this mitosis steppables also has this update attributes function that gets called automatically by CompuCell when there is a division. And it goes through the cells that participated in the division, so the mother cell and the child cell. And in there, the parent cell has the special name of self.parent cell, and I'm having its target volume. Say the initial volume was 60, so when it gets to 120, it should divide. But to get to 120, its target volume should be around 120, more than likely it's already beyond that. So I'm just having that back to 60 or near 60. And then I'm cloning all the attributes of the parent to the child, with that clone parent to child function. And there is a clone attributes that is a more involved function that then you control exactly what the child inherits from the parent. Yeah, we could use links, I guess, which is something that will be covered, Julio? Yes. So links, as the name suggests, we add a link in between two cells and they have a spring potential in between them. So then you set a maximum distance for the thing to break, a equilibration distance, and everything else. So yes, that's one way that I can think of. There might be other ways. Why is it not here? Okay, Maciek? Why mitosis is its unique class?
It's not biological, right? In biological, so you have two daughter cells, right? But the cell object that gets created after mitosis in CompuCell gets called child cell, I believe, and you have references to it. And then this class also has uses C++ code, which you don't know about, right? When you call self divide along, or cell divide, no, divide cell random orientation. What happens there is that there is a call to C++ function that is hidden from you, right? If we didn't use this class, you would have to actually create or get a hold of C++ mitosis steppable and call directly C++ function, and it was just too much. So the reason why there is separate classes just for simplicity, so that you don't have to deal with all this nonsense. That's just like, you know, you can do modeling and yeah.
So these methods are actually defined in the C++.
Yes. Yeah. Yes, because when you do mitosis, you know, first of all, you have to compute axis. You know, the major, minor axis. Then you have to do division, and there's just a lot of, you know, bookkeeping going on. And in Python, it will be quite slow, right? I mean, those simulations, I mean, if you have one or two cells, you know, maybe you wouldn't notice the difference, but you have lots of cells, then it makes a big difference. So, so that's the reason. And yeah, that's the reason.
So to track lineages, we'd have to use cell dictionaries. So one thing that we haven't talked about yet is that you can add as much information as you want to any and all cells. So Yeah, let's do lineages. That shouldn't be too bad, hopefully. So here in the beginning, the start function, when I'm going through all the cells, for each of them, I'm gonna give them a dictionary, so cell.dict, and I'm gonna name that lineage. And that lineage is gonna be a list of all its ancestors. So I could either have it as an empty list, or instead I can have the list be the list of all its ancestors and itself. That's gonna be easier for me. So I'm gonna initialize that cell dictionary lineage as a list with the cell ID. So its own cell ID in that list. Is that big enough? Yeah. So then, I'm gonna go to the mitosis, and here on the, yeah. So here on the update attributes, after the clone to parent to child, so the clone parent to child is gonna take care of cloning the dictionary to the child already. So the only thing left for me to do is go to self.child cell dot dict lineage and append the child cell ID. And that tracks lineage. Then to access that, you could have in the we could have here in the let's have the cells that die scream to their ancestors that they have died. So print, when a cell turns necrotic, print for fathers I am no more. New line. And then its whole dictionary of lineage. Oh, and here's the final state of that thing. Let's check if that's the one I changed. Yep. So it's gonna take a while for anything to be printed because I'm only printing when they turn necrotic. Yes, yes, there are diminishing returns. Yes, there is a limit that has to do with the cellular POTS model algorithm, but the guts of CompuCell take care of that to make sure things don't go wrong. And it's most useful if you have chemicals, because those can be parallelized ad infinitum with no issue. So in my simulation, since I don't usually have chemicals, I don't even bother. But 2, 4, 8. The limit on the, how's the limit on this? Because you allocate part of the grid to each core for the plots. But I don't remember how that relates to the number of cores. Maybe a bit, yeah, because of the chemical field mainly. And it would also go faster if I set it to update the cell fields every 10 Monte Carlo step instead of every step as it is now. So yeah, I'm getting a new screen every. Mm-hmm. Yeah. Yep. There we are.
Okay, now what's strange is that you have 3 colors on yours.
Yeah, that might be a Mac thing. Well, Why won't they die? I want them to scream to their forefathers. You did? Okay. Mm. But yeah, the main idea of this exercise is to actually get it to have 3 layers and stay with 3 layers while some die and some proliferate. Mm. Right now, with the parameters I have, everything will turn quiescent and then maybe die. Yeah. Yes, so to grow and proliferate, what I'm doing is just each time step, I'm increasing the target volume by 1. And then when they reach a volume twice the starting volume, they divide. A good exercise for tomorrow would be to make the growth be proportional to the uptake, for instance. Yep.
And that's for both the proliferating and quiescent?
No, that's just for the proliferating. Yeah, yeah. So yeah, the supply is a constant value at the borders of this one. So they are just consuming more than the supply can give. No, but there is the color plot. But yeah, the idea is playing around with the thresholds and uptakes and whatnot to try to have the 3 layers. I have the,
So I should see here from this color that the threshold is around 50 or so.
yeah, you can actually see the threshold on the Python. It's going to be on the start function.
The proliferation threshold 65. The 65.
Yep. And now they are dying and screaming to themselves that they have died because none of them had parents.
If they have parents, so it would be a different output.
Yeah, because I'm telling them to print the lists, the list of the lineage, and they are in the lineage itself. So if they had parents, it would be the idea of the parent, the great-grandparent, et cetera, parent themselves. I have the same simulation with medium as the supplier at a constant value. And that one, the tumor grows more and actually reaches a steady state. I'm gonna just tell that one to run. type change loop, one thing that you can see there is both for when they turn necrotic and when they turn quiescent, I'm resetting the target volume to be their current volume. Because the proliferating cell, okay, is growing because I'm growing its target volume, but much more than likely, it's gonna be way below its target volume and have not reached it yet. So what I'm doing here is making sure that a cell that has turned quiescent doesn't keep growing until it reached that target volume. So I'm just resetting its target volume to be its current volume. And in the case of the necrotic cells, I've also increased the lambda volume to 100 because necrotic cells, they are shrinking each time step by 25%, the target volume. But because of other cells actually pulling them, they are not able to shrink on this simulation. I've seen another simulation that they do actually shrink quite fast, and that kind of keeps the tumor a certain size after a while. So that's why I tried cranking up the lambda volume of the necrotic cells here to really make them disappear. To not too much success. So, no, the quiescent cells stay as they are. But in here, I'm going through the proliferating cells and the necrotic cells. And each time step, I'm multiplying its target volume by 0.75. Because the necrotic cells are dissolving. That's a way to think about it.
So when you trigger the necrotic cells to observe the volume?
The moment they become necrotic, I reset the target to be their own volume, even though it definitely would never have happened from a proliferating cell to go to necrotic. I still have that there as a safeguard. Because the quiescent cell already are around their target volume, and so if going from quiescent to necrotic, I don't really need to reset the target volume to be their current volume. But just to be safe, I am. Yeah. Yes. So the necrotic cells, I'm making them disappear slowly because just making them disappear causes an implosion. But I was really trying to make them disappear in the simulation, and I wasn't really being able to because they were still being pulled into existence by the contact energies. Yeah. Yes, there is a function in CompuCell to delete a cell and that turns into medium, but that would also create an implosion. So I just wanted them to shrink and pull the tumor back inside, back towards the center. And this if cell volume stuff was another attempt at achieving that. That was less than successful. Well, this is not needed. And probably I should have removed that before. Yeah. Well, diminishing the target volume is not a hack. It's them being dissolved and the quiescent cell getting them out and pooping them outside, whatever. So that's why I'm diminishing the necrotic cells target volume each time step. Since they are shrinking and they are in the inside of the tumor, the only thing that can, you can have medium appear from outside the tumor into the inside of the tumor because there's a copy range. A pixel copy only happens with its neighbors. So what? Yeah. Yeah, what I could do is have another cell type named lumen that has some different properties than medium and turn that into one gigantic lumen cell. That would probably make more sense. But if the center here was necrotic and trying to shrink, it would actually try to pull the quiescent back inside through copies at the border of necrotic and quiescent. And yes. Yes. Yeah. So the quiescent that is right next to the necrotic will increase in size because of the negative pressure inside, but it doesn't really want to. So kind of will, ideally, it would make a wave of cells coming inside. So the nearest quiescent will grow a bit into the inside and then shrink a bit to the next layer of quiescents that would have grown inside, and so forth.
But what you need to do is you're freezing the necrotic cells at the original volume, right? With the lambda of 100.
Yeah, but immediately after I'm decreasing, so I'm setting their target volume to be their volume. Then immediately I'm resetting their target volume to be 75% of that. And in the next step, 75% of that. So that if statement I had there was me attempting to go faster. Yeah. Yeah. Yeah, because really I should have taken out before since it didn't work.
Now, is it necessary? I mean, so what you're doing is you're basically changing the, in your stepping, changing the target value twice. Once there's the original value, and then a couple of lines later, there's a 75%.
Well, it's only gonna enter this part of the code when it turns necrotic because of this. So if the cell is not necrotic, it can go in here, change its type to necrotic, and reset its target volume. But after it's already necrotic, it's not gonna enter here. But let me show you a nicer simulation from one of James' students last semester. So yeah, these are the kind of stuff that it can make happen with the tumor spheroid. He has immune cells attacking the tumor here. Those are the little blue things. So yeah, the top GIF is exactly the case where you have medium as the supplier, constant flux, and then you have a oscillating tumor after it grows over the maximum tumor size. And Zoom people, you seem to be getting a slideshow instead of a GIF, but sorry. So in here, just by having medium as the supplier instead of the edges, the tumor already has been able to grow way more. And there has been waves of growth in the proliferating number. But again, playing with supplies rate and uptake rate, diffusion length outside and inside the tumor, the one with the edges as supplier surely can reach the same state as here. Would probably be a matter of increasing the diffusion rate and then the decay rate as well, just to make things the same, so that the oxygen reaches the border of the tumor faster. And that's related to the issue on the beginning of my talk of what's the faster simulation you can make. So the problem with the edges supplier on this simulation is that oxygen is not reaching fast enough. But I still want to keep the length the same. So I up the diffusion to get it to reach it, and up the diffusion to keep the length. But the equilibration time is going to be less. And the diffusion time from the edge to the border of the tumor will also be less, because that's inversely proportional to D and doesn't care about gamma.
Now, these simulations you have, at least, not this other guy, but yours are basically point symmetry.
Yeah.
So you could just do this one
Yes.
problem.
Yeah.
At least lower.
Yeah, I could.
Maybe using OptiSci.
Yeah, well, CompuCell doesn't do real 1D really well because of, I guess the cells would be too fragmented in the end if you had just a single line of pixels. Or maybe not. Well, I guess it could work. But I've never seen cellular POTS model simulations on proper 1D. Maybe 1.5D with huge on one side and thin on the other. But
Yeah, or looking at periodic boundary conditions.
yeah. Yeah. Yeah, I could simulate just just this. Then it's just a matter of setting only these edges as the supplies of oxygen and setting everything else as periodic. But periodic for the chemicals and not the cells, because on CompuCell we are allowed to do that. We can have it be periodic for cells and not chemicals, chemicals not cells, periodic for both or neither. Because if I had the quarter here and it be periodic for cells, well, they are in contact with that one as well. Yeah, yeah. I think to actually make that, it shouldn't be periodic. Yeah. Yeah, yeah, that's not you. You. So yeah. Yeah. Well, the expression is a constant in this case. Yeah. Yeah, if it were 100 times x times y, then it would be 0 here Yeah, 100 times 256 squared there. The easiest way is when you're creating a project, then you have mitosis here. If you already have a simulation, then I guess it's harder. Don't know if the way I did this one, because I forgot to select mitosis at the beginning. I created a new dummy simulation with mitosis and copied from there. Yeah. Yeah, it should be. But yeah, feel free to play around with the parameters, take a break. I've gone through all my material.